Thank you for allowing me to speak about algebraic matroids, disguised by a fancy title. But before I get to the meaning of this fancy title, I'll first define algebraic matroids. So, if K is a field and L is an extension field of K, you can look at a multi-subset of elements of L, and there are some algebraic relations between them. So we call a set dependent if there is a polynomial over K relating these elements of L. So it's quite an old theorem that this gives us a matroid, and we call E an algebraic representation of this matroid over K. So just an example, if our field is the field of two elements and we extend that field by A and B, then we can take A, B, A plus B, and A plus B squared as our algebraic representation of some matroid. Well, some of the relations that we get are listed here. For instance, the relation F1, 2, 3 on the bottom right holds because, well, A plus B plus A plus B is 0 over GF2. And the matroid that this representation represents is U24, the uniform matroid of rank 2 on 4 elements. So what do we know about the class of algebraically representable matroids? Well, at first it seems like a very nice class. I mean, its minor closed. You can add elements freely on flats. It contains the class of all linearly representable minors. And I could name a few more nice properties of this class, but it's actually not that nice. Because even a simple question like, is it closed on the duality? We don't know the answer to. And similarly, I don't know of an algorithm that tells me whether a matroid is algebraically representable, well, a finite algorithm that is. So these are all questions that I would like to answer, and yeah, while I cannot answer them to you in this talk, I hope I'm giving you something to work towards the answers to these questions. So we can simplify an algebraic matroid, or at least an algebraic representation of a matroid. And by simplify, I mean we make it a linear matroid. So how do we do that? We apply derivations, and then we get a simpler linear matroid. So we have this example again. I just replaced the b by b to the third in the third representative. And this is an algebraic representation of U24. Now what do? I create a matrix, and in the first row I take the partial derivative of everything by A, and in the second row I take the partial derivative by B. And this gives me a matrix, well, I take its row space, over L. And now what I do is I fill in a sufficiently general point for A and B. What do I mean by sufficiently general? Well, I want as few extra dependencies as possible. So in general, such a point may not exist within the original field K. In this example, the point 1, 1 suffices. Okay, so this is now a linear representation of a matroid where the first and the fourth elements have become dependent. And, well, the linear representation that we obtain in this way, we will call VEX. Yeah, so we want to do this on a large scale because we've thrown information away about the original matroid. For instance, the fact that the elements 1 and 4 were a basis. So now we need some tools to do it on a large scale. So if K is an algebraically closed field of non-zero characteristic, then K has an automorphism sending an element of K to its pth power. And now a few technical definitions. So on subsets of K to the E, we define first a Frobenius action. So alpha x, well, I take the ith coordinate of each vector in x, and I take it to the I take the Frobenius automorphism alpha I times of it. So that gives me another set. And similarly, we have deletion. Well, it's not matroid deletion yet, but it's similar. We just throw away the ith coordinate. And we have contraction. So we first take all vectors in x that have a 0 on the ith coordinate, and then we throw it away. And by bold face 1, I denote the all 1 vector. So we have this Frobenius action, and we can also apply it to our extension field. I mean, we had these extra a and b. We can also take a to the power p and b to the power p. And it has a nice property that if E is an algebraic representation of a matroid, then after applying alpha with this above action, we still have an algebraic representation of the same matroid. So we are going to take our original algebraic representation, and for all integer vectors alpha, we're going to look at the algebraic representation we get and the respective linear space we get from that, and that will give us a Frobenius flock. And a theorem we recently proved with Jan Drijsma and Rudi Pendavingh is that there exists a single point that works for all, that is sufficiently general for all integer vectors alpha. And it satisfies some properties that, well, I won't go over them yet because it's not really enlightening yet. So, yeah, if a map satisfies these two properties, so a map from the integer vectors to r-dimensional subspaces of K to the E, then we call V a Frobenius flock. Now, if we take these linear representations of matroids we have linear spaces for each integer vector alpha. And if we forget the linear representation, but only remember the matroid it represents, then we get a matroid flock with similar axioms. And if you've seen my talk about this last year, then we did not know yet that matroid flocks arise in a different way as well. And that's what we're going to do now. So we start off with matroid valuations. So a matroid valuation is a map from R subsets of E to the real numbers, including infinity, with a submodularity condition. So the first observation is that whenever nu of B is finite, well, all the B such that nu of B is finite gives a matroid. Well, this is not very hard to see because if we can prove the base exchange axiom, if these two are both finite, then, well, neither of these can be infinite. Okay. And if we have a matroid valuation, we can create basis sets for each real vector, but we are in fact only interested in the integer vectors if we are going to generalize it to matroid flocks. And that is, you take the maximizers of this function, and EB just means the vector with a 1 on the entries that are in B and a 0 everywhere else. So the maximizers of this function give the basis set of a matroid. And again, it's not hard to see with symmetric base exchange. So if we have two bases, E in one but not in the other, then since nu is a valuation, there exists such an F satisfying this submodularity. And then we just rewrite. So we move a term alpha E from left to right and a term alpha F from right to left. And we apply this submodularity and we get the functions up here for the different bases. Well, these top two were maximizers. So since we have a lesser equal here, these two must also both be maximizers, proving a base exchange. Okay, so these are the basis sets of a matroid, and we can consider the map M nu, assigning to each integer vector a matroid on E, defined by our basis set. And then we have shown that these matroids satisfy this property, which you should recognize as the properties that define a matroid flock. So why are these properties satisfied? Well, the first condition is not that hard to see. If a set of bases maximizes this function for alpha, well, adding the all one vector to alpha is not going to change the set of maximizers. And the second property says something like, if I raise the value of alpha at the ith coordinate, then bases that contain I are somehow more likely to be in the basis set. Okay, and a key observation is that each matroid flock comes from such a valuation. So this is a nice picture. It's a four-dimensional picture, but I modded out the all one vector. And this decomposes R4 into cells, where each cell corresponds to a matroid. So all the points alpha in a cell have the same matroid. So these maximal cells out here, these three-dimensional cells, they correspond to the matroid where there is only one basis. Whereas these points here, they are two connected matroids. So this is in fact a tropical linear space. Now finally we get to the Lindström valuations. So we've seen that if we take a Frobenius flux, so a collection of vector spaces for each integer vector, and we take their matroids, it's a matroid flux. Now if this matroid flux happens to come from valuation nu, then nu is the Lindström valuation corresponding to this algebraic representation E. So a Lindström valuation always comes from an algebraic representation. So let's see this example again. Okay, so the Lindström valuation for this example, well, it assigns 0 to each basis except 1, 4, because 1, 4 was not a basis of the linear representation we had after taking the derivations, and it will be a basis somewhere else. Okay, I just want to mention that Dustin Cartwright found a direct formula for the valuation given an algebraic representation, but I don't want to translate that right now. Okay, so algebraic representations give rise to Frobenius flux, which give rise to matroid flux, which are in a one-to-one relation with valuations, well, integer valued valuations. And this scheme helps us to prove that matroids are sometimes not algebraic. So in 1985, long before I was born, Lindström proved that Lazarson matroids, of which the Vámos is a special case, are algebraic if and only if the characteristic is 2. Well, how could we do that more easily now? We know that the Vámos matroid only has a trivial valuation. That means all bases of the Vámos matroid come together in one point. And that means that some point of this matroid flux is the Vámos matroid. And it also means that since there's a Frobenius flux, if it's algebraic, that we have a linear representation of the Vámos matroid in there. But that can only happen in characteristic 2. So if the Vámos matroid is algebraic in characteristic 2, in characteristic P, then P must be equal to 2. And, well, Gordon had a similar result for reed geometries in 1986, and in view of time, I'll skip that for now. So if nu is a valuation such that the matroid of nu is a connected matroid, then we can talk about the central points. So in this picture over here, these 2 points here are the central points that correspond to connected matroids. And up to the all one vector, there's only a finite number of them. So what we've done is first of all prove that if you somehow fill in the central points, then they determine the rest of the flock completely. And we also know a characterization for when exactly this happens. And this gives us extra tools to attack algebraic representability. So we have a notion of duality for matroid flocks. We can simply take the dual of the matroid at alpha and put a minus sign in front of it. But for Frobenius flocks, we have almost duality. We can do the same, but it's no longer the Frobenius automorphism that's working, but it's inverse. And it's an interesting question whether the class of Frobenius flock representable matroids is closed under duality. So yeah, this whole framework gives us extra tools to investigate Frobenius flock representability based on just valuations. And hence also to attack the problem of algebraic representability. So to finish off, I want to show that our methods are not omnipotent, because the Vámos matroid is a non-algebraic matroid. And how do you see that? Well, in an algebraic matroid, if you have such a prism here, these three lines, they will intersect in a point. And Vámos has two of these prisms stacked upon each other. So these two lines here meet in a point. Oh, but that means that these two lines here, they lie in a plane. And, well, this is all assuming there was an algebraic representation. So we get an extra dependency, and hence the Vámos is not algebraic. But the Vámos has a lot of valuations, and many of them can be represented by a Frobenius flock. So we still need to find a way to incorporate Vámos type non-algebraic representability in our Frobenius flock methods. And yeah, there's still a lot that can be done. So thank you.
Any questions?
Can you compute these valuations easily and sort of go through its hierarchy?
Yes, I can compute valuations, but not for too large matroids. So for matroids up to 8 elements, if they are not too close to the uniform matroid, we can do it, but any larger than that, it becomes difficult. So for instance, the tic-tac-toe matroid, which is a nice candidate to be a counterexample to being closed under duality for algebraic matroids, it's on the boundary of what we cannot do.
Any other questions?